Hi everyone, now we are going to learn about the photon emissions by hydrogen atom. So what is actually photon emission? So the photon emissions is happen when the electrons is transferring from a higher energy level to a lower energy level. So the energy actually lost in energy, where this loss of energy is actually being emitted as a photon. So it will emit photon when it's transferred from higher orbit to a lower orbit. So this emissions of photon has the energy which is equal to the difference between these two energy levels. So if we let this one as EA, the lower energy level as EA and the higher energy level as EB, so your HF, the energy of photon that being emitted by these transitions of electrons will become EB minus EA. Means using the higher energy level minus the lower energy level. In other words, your E energy level, which you will have learned in your previous lesson, where En is equal to negative 0.6 electron volt divided by n squared. So this one is in electron volts. If you want to put it in joule, no problem. So I use electron volts for this example. So you can try with joule. So if the orbits, the quantum number of EB, I let it be B, and the quantum number for EA, I let it be A, let's say. So this equations, EB will be rewrite as 13.6 divided by B squared. And for energy level in the orbit A, so the quantum number, I let it be A. So you will have these equations. So factor out the 13.6 electron volts. So you will get your equations as 1 over A squared. So become positive. So it's 1 over A squared minus 1 over B squared. So this is the energy that emit from the photon of energy that emit from the transitions of electrons. So this is your energy release. So the energy of photons due to the emissions of electrons. So let's say you want to calculate the frequency of the photon that being emitted by the transitions of electrons. So rearrange this equation. So you move your H to the right hand side, then you will get 13.6 EV over H, 1 over A squared minus 1 over B squared. So this is the frequency of the photon. Okay, frequency of photon that due to the emissions of photon energy or the emissions of photon from the transitions of electrons from the higher orbit to a lower orbit. So in other words, because it is a wave nature, okay, it has a wave nature because wave particle wave duality, we have wave particle duality. So we can calculate lambda, okay, the lambda of a photon. So how do you calculate the lambda of photon? So we know that the electromagnetic wave has speed which is equal to the speed of light is equal to f times lambda. So lambda will be equal to c over f. So substitute inside here. So you will get that f is actually c per lambda. Your f will be equal to c per lambda. So substitute inside. So you will get your 1 over lambda is equal to 13.6 electron volts times Hc 1 over A squared minus 1 over B squared. So this is how you calculate your lambda, the wavelength of photons that emit by the transitions of electrons from higher orbit to a lower orbit. So there are a few series. We have some name for the emissions of electrons. We have some series for the transitions of electrons from higher orbit to a lower orbit. There are few series that we given name due to the final stage of the transitions of electrons. Okay, the first one we call it as a Lyman series. Where the Lyman series means that when the electron move from a higher energy state to ground state. So means that the final positions of the electron is in ground state. Okay, so it move finally to ground state. So this type of transitions we name it as Lyman series. Okay, any transitions from a higher orbit to ground state. So for Lyman series, it will emit a photon which has F equal to, so we have F equal to, this is a general equations in order to calculate the frequency of the photon emissions. So substitute now because the final state is n equal to 1. In other words, A will be equal to 1, your B will be equal to n. N will be the higher energy state. So when you substitute inside, so you'll get something like this. Okay. So the B will be equal to B squared, or you want to put it as n squared, yes. So B now must be greater than 1. So the final product of the transitions of electrons must be in ground state. So this one is the frequency of your photon. Okay, if you substitute the value of H and B inside here, let's say now, okay, wait. So if you want to have more, so this one I put it in n because here is using n here, so I put it in n. So this one is n. Okay, let's say now your n. So initially the electron sit in first excited state, so n equal to 2, and then it moved to n equal to 1. So the energy of photon that emitted through these transitions will have equal to 10.2 electron volts. Okay, the frequency will have 2.46 times 10 to the power 15 hertz, and then you will have the wavelength which is equal to 122 nanometer. So if you notice here from this graph, okay, from these transitions, the arrow, this one has the smallest transitions. So in other words, this one will have the minimum energy of photon produced. So this one will have minimum energy produced when it's transferred from first excited state to ground state. And then because F is directly proportional to the energy level, to the energy that in a photon. So if you have minimum energy, means you will have minimum F for these transitions. So minimum F means you have maximum lambda. So this one is your maximum lambda for Lyman series. In other words, for Lyman series, the minimum energy is 4 on 10.2 electron volts. The minimum frequency is 2.46 times 10 to the power 15 hertz, and the maximum lambda will be equal to 122 nanometer. So if you look at this table, the one with that maximum energy, this one is the maximum energy. So the maximum energy happens when the transitions of electron is from infinity to ground state. So it means that this transitions, if you look at this, it has the highest or longest transitions between the electrons. So it will emit the maximum energy of photon. And then it has maximum frequency of photon in Lyman series. While when we have maximum frequency, then we will have minimum lambda for Lyman series. So if you look at this one, the energy of the photon is actually in between 10.2 electron volt and also 13.6 electron volts. So the energy due to the Lyman series, in Lyman series, the transitions of electrons due to Lyman series, the energy in the range of 10.2 and 13.6 electron volts. Then for frequency, it is fall between 2.46 times 10 to the power 15 and 3.30 times 10 to the power 15 hertz. So in other words, it is in between. The value of photons, the value of frequency of the photons for Lyman series is in this range. Well, for wavelength, it will be in between 91 nanometer and 122 nanometer. So it means that for Lyman series, it will produce the photon that with wavelength in between this value. The range of the photon is between this value. So if you look back to your electromagnetic wave, the table of the electromagnetic wave, which you have the lambda, you will notice that this lambda, this electromagnetic wave that fall in between this lambda is actually ultraviolet. Means that for Lyman series, it will emit ultraviolet electromagnetic wave. Okay, for Lyman series. This one is called Lyman series. So what if the electron is transferring from higher energy state to the first excited state? So when we say first excited state means n equal to 2. So this one is called Balmer series. So for Balmer series, it actually transitions from a higher orbit to the first excited state. So what is the frequency? How do you calculate it? Still here. So your A now is equal to 2. And then your B is n. So substitute inside, your F will be equal to 13.6 electron volt divided by H. So now it is A is 2, so you get 1 over 4 minus 1 over n squared. So if you substitute n in this value, 3, 4, 5, and infinity, so you will get the range of your photon energy, the range of the frequency, and the range of your wavelength for the photons is in this type of value. So in other words, the minimum energy that emit from this Balmer series will have this value, and then the minimum frequency due to the transitions in Balmer series will have this value, 4.56 times 10 to the power 14 hertz. Then for the maximum lambda for the Balmer series will be equal to 658 nanometers. So this one is the least or the minimum photon energy emitted by the Balmer series. Well, for the maximum energy due to the transitions in Balmer series, this one is the maximum energy that produced by the Balmer series. So in other words, the photon energy, the maximum photon energy that emitted through this Balmer series will be equal to 3.40 electron volts. While for the frequency, the maximum frequency, this is your maximum frequency, which is equal to 8.21 times 10 to the power 14, and this one will be your minimum lambda in Balmer series, which is 365 nanometer. So in other words, we can say that the emissions of photon in Balmer series will have the energy range in 1.89 electron volts to 3.40 electron volts. It cannot be fall outside this range, no. Okay, it must be in between this range. And then the frequency will fall between the 4.56 times 10 to the power 14 to 8.21 times 10 to the power 14 hertz. While lambda must fall between 658 nanometer and also 365 nanometer. So it must be produced within this range. The photons that emit through this series, Balmer series, it's in this range. So if you refer back to your electromagnetic table, wave table or electromagnetic spectrums, so you will notice that this lambda is actually the visible light of your electromagnetic spectrum. Okay, so this range is actually visible light. Means when the electrons transit from higher energy level to first excited state, where we call it as Balmer series, then this Balmer series will produce visible light. Okay, now we have the third understanding for the photon emissions by hydrogen atom when it moves from higher energy level to second excited state, where we call it as Pascal series. So Pascal series means the energy transitions from a higher orbit to second excited state. So now you substitute A is equal to 3 because now final state is in n equal to 3 and B is equal to n. So you will reduce this formula is equal to 13.6 CV over H 1 over, so this A now is 3, so it's 1 over 9 minus 1 over n squared. So this one will become the formula for your Pascal series, the frequency of your Pascal series. So by substituting the equations in the formula, so you will get this table. So in other words, for photon energy emissions through Pascal series, then you will produce this as your minimum energy produced. This one is your minimum energy, and then this one is your minimum frequency, and this one will be your maximum lambda. So from the transitions of 4 to 3. Okay, if the transitions from infinity to the second excited state, then it will produce the maximum photon energy and also maximum frequency of that photon and minimum lambda of the photon emissions. So in other words, your energy due to the Pascal series, the photon emissions due to Pascal series is fall between 0.66 electron volts and 1.51 electron volts, while the frequency will fall in between within 1.59 times 10 to the power 14 Hertz and also 3.64 times 10 to the power 14 Hertz, while the lambda will fall between 824 nanometer and 1887 nanometer. So it will fall in between this range. So your Pascal series will produce a photon set with this range of energy, this range of frequency, and this range of lambda. So if you refer back to your electromagnetic spectrums, then you will get this range of lambda is actually infrared. Okay, so it means that for Pascal series, it will emit the photon which we call as a infrared photon. So this table will help you to finalize the series based on the final level of the transitions of electrons. So for when the final state of the electron is transferred from higher energy level to ground state here, this is ground state, n equal to 1, that we call it as a Lyman series. And for Lyman series, it will emit ultraviolet. Well, for Balmer series, the final state is 2, which is your first excited state. So it will release or emit the visible light. Well, for Pascal series, the final state is 3. So the emissions of photon is infrared. Well, for bracket series, the final level is when n equal to 4. So the emissions of photon is infrared. So for one series, the final state is the n equal to 5, where is your fourth excited state. So the photon is called infrared. So this is the general name for the series of emissions of photon when it transfers from one state to another state. So it has the specific name. So you have to remember this one for your exam. I hope you can understand what I've been teach you. So that's it for this lesson. See you in my next video.